Hello everyone, welcome to Numerical Methods class. Today's video have the chapter 5, which is about the roots of equations. Basically, we want to use numerical methods to be able to find the roots of some equations. And for those, there are some methods that we will discuss. And in chapter 5, we will talk about the bracketing methods. And let's look at these bracketing methods in this chapter. We can actually find the roots of some equations using analytical formulations. For example, for a quadratic function which has a second order variable, as you can see over here, we can simply use this equation. You are already familiar with this, and we can find two roots for this kind of equations. There are also many other functions, but for them, usually we cannot find the roots easily, or maybe sometimes it is really not possible to find the roots using this kind of analytical equations. For example, this function, which has an exponential and an x, this cannot be solved analytically to find the roots of this function. Basically, finding means we will equate this to 0 and try to find the x value which gives the 0, as you can see over here for this function as well. This is equal to 0, and we are trying to find the x values which makes this equation equals to 0. So, if we cannot solve analytically a function, then we need numerical methods to find the roots of such equations. In engineering areas, roots of equations are really important in different physics. For example, for heat balance, the temperature and time and position are the variables, and the parameters are the thermal properties of material and geometry of system. And if we have a physical equation, we need to find the roots of that equation so that we can find these variables. And if we cannot solve these problems, we need to use some numerical approaches. Similarly, for mass balance, we will have concentration or quantity of mass as the dependent variable, time and position as the independent variable, and the parameters are chemical behavior of material, mass, transfer coefficients, and geometry of the system, etc. For a force balance, magnitude and direction of forces are the dependent variables, and time and position are the independent variables, and strength of material, structural properties, geometry of system are the parameters. For an energy balance as well, changes in the kinetic and potential energy, states of the system, and the time and position are the variables, and thermal properties, again mass of the material and system geometry are the parameters. For Newton's laws of motion, which is F equals m times a, acceleration a, the velocity v, or the location as are the variables, dependent variables that we want to find, for example, and time and position are the independent variables. So for these as well, we need the mass of material, system geometry, dissipative parameters such as friction and drag coefficients, etc. And for Kirchhoff laws, currents and voltages in electric circuits, maybe this is not related to mechanical engineering area too much. This is still in the engineering area, so still we can have some equations based on these variables. And for all of these, simply we need to solve some equations to find the roots. And if it is not possible, we need to use numerical methods. And before moving on to the numerical methods to solve the roots of equations, we need to talk about some terms. For example, the explicit and implicit variables. An explicit equation or function can be directly solved for a variable. For example, for the parachutist example that we mentioned in the earlier chapters, the velocity can be calculated by using this equation. And in here, v is an explicit variable because it's just simply solved by just simply adding the terms here or replacing the terms by the variables. We can easily find v. So this is explicit, easily find them. But the question arises, what if we know the velocity, we know this value, and we want to calculate the drag coefficient, for example. So we want to calculate this or another parameter from this right side, t, for example, or c. So the question here is about c, that's why we will continue with c. If we want to find this, then we need to solve this equation by isolating this c. So we need to isolate c. But isolating C is not possible. You can try this. Really, here there is a C and here as well. It's not easy or possible to isolate it. So what we need to do is simply, because we are not able to solve this analytically, because we are not able to isolate this, we need to use some numerical methods here. And in this case, actually, if C is not directly solvable, then the function becomes implicit equation or function. So we have a variable which is not able to be isolated, let's say. That's why it is an implicit, the C here is an implicit variable. But V is explicit because we can easily isolate it and find the solution directly by simply replacing the values. So for the implicit equations, to find the implicit variable or solve this implicit equation like C, we use a numerical method, and for this purpose, to be able to apply a numerical method, we simply write the equation as follows. So because we are not able to isolate C, we simply say, okay, this function is about C, fc, and we just simply move this v value to the other side, and we have this function equals 0 and want to solve this. So fc is 0 now. That's why we want to solve this function to get the roots of this equation. And C is the direct coefficient that we want to find, for example. We also have two equation terms that we need to define before starting to explain our numerical methods. And these are called algebraic equations and transcendental equations. So the algebraic equation is simply a function given by y equals fx. And if this is equals 0, and I mean if we can write this function like this, equals 0, then this is simply an algebraic equation. And polynomials, for example, that we use in regular life in mathematics, these are algebraic equations. Here a's are the constants, which are here some examples of constants, and n is the ith order polynomial in x. So this is the order of the polynomial. These are algebraic equations. And there is also transcendental equations, and these are the equations which are not classified as algebraic equations. So for example, the trigonometric, exponential, logarithmic, or other less familiar functions, if the polynomial or the equation includes these, then it is called a transcendental equation. As you can see over here, we have an ln logarithmic value and or sinusoidal and exponential parts. So these are transcendental equations. This is important because we need to solve these equations with different methods, and we will explain the numerical methods in the following slides. The numerical methods to find the roots of equations are actually plenty, and we can classify them into two groups based on the finding of real and complex roots. The first one is determination of the real roots of algebraic and transcendental equations. And these methods are usually designed to determine a single real root value. Real means like actual root without any I, the complex root part. And these can be found based on its given approximate location. And chapter 5 and chapter 6, the bracketing methods such as graphical, bisection, false position, and also in chapter 6, the open methods such as fixed point iteration, Newton-Raphson and second methods. These are the methods to use to determine the real roots. And in the second class, we can say that the methods to determine all real and complex roots of polynomials are in this class. And these methods are specifically designed for polynomials especially. And they determine all the roots rather than determining a single real root. And chapter 7, roots of polynomials, have this classification. These methods in this chapter are actually in this class, let's say. So we will start with chapter 5 to determine the real roots of an algebraic or transcendental equation with the bracketing methods, then continue with chapter 6 open methods, then we will move on to chapter 7. And in this chapter 5 we will be focusing on the bracketing methods.